Welcome to Lesson 2 in our Study of Time series. I would like to encourage all of you to comment right here on this blog. Introduce yourself. Say what you think is good, what you think is bad, what's going too fast, what's going too slowly. Give your solutions to some of the problems that get assigned. Just talk amongst each other. I think that would be excellent. Comments will be moderated mainly because I want to keep spam off this blog. We're going to start by looking at some of the problems I gave last time. I'm going to give you solutions for 3 of the 4 problems. They're solutions I came up with, and they're not necessarily the only solutions. Let's start with the first problem, which is devise a time series, which is white noise, but it is not IID, that is to say, independent identically distributed. Consider this probability function. There's a 2/3 chance that x will take the value -1. And there's a 1/3 chance that x will take the value 2. Because of this probability function, the expected value of x is 0. The expected value of x squared is 2, so the variance is also 2. Now consider this different probability function. There's a 1/3 chance that x will take the value -2, and a 2/3 chance that x will take the value 1. Once again, the expected value is 0. Once again, the expected value squared is 2, so once again the variance is 2. Now, let's devise a time series process. It's going to be random, and the probability function is going to alternate between P1 and P2. Because those two probability functions have the same mean and the same variance, that means that for each and every value, the expected value is 0, the variance is 2. It's going to be the same for each and every one. But for different values, xj and xk, where j is not equal to k, the expected value of xj times xk is going to be 0. So the covariance of the two values is going to be 0. Therefore, it is white noise. The mean and variance is the same for every value, and the covariance between different values is 0. That's kind of the definition of white noise. But they don't all follow the same distribution. Even and odd values follow a different distribution, so they are not identically distributed, and therefore not IID. So this rather simple example is a time series process which is white noise, but it is not IID. The next problem was to devise a time series process which is weakly stationary, but is not strongly stationary. Well, there's a relatively easy answer, and that is the same time series as for the previous problem. We showed it was white noise. Well, white noise is weakly stationary, so that process is weakly stationary. However, the probability density function is not time translation invariant. It's different between even and odd values. Therefore, it is not strongly stationary. Finally, I'm going to take a look at problem number 4. I'm leaving problem number 3 to you. Problem number 3 was to show that the covariance between two quantities doesn't change when you offset either one or both by a constant. So I want to show that the correlation between random variables x and y cannot be greater than 1. It has to be less than or equal to 1. Well, we already know that the correlation between x and y is equal to the correlation between x minus some constant and y minus some constant, maybe a different constant. So I'm going to begin by subtracting the mean value from each one. So we can assume that x and y have mean value 0. If they don't already, we can make them so. And we haven't lost any generality. Now, in that case, the covariance, not talking about the correlation, but the covariance, is just the expected value of x times y. I don't have to subtract the expected value of x times the expected value of y, because I know they're both 0. I'll call that gamma, and I've just given the name gamma to the covariance. Now I want to define a new variable. I'll call it z. It will be equal to y minus gamma times x divided by the expected value of x squared. Now do keep in mind that y is a random variable, x is a random variable, so z is a random variable, but the expected value of x squared is not a random variable. It's just a number. It's a property of the probability distribution. Well, like x and y, z will have mean value 0. That's because the expected value of z is the expected value of y minus gamma divided by expected value of x squared times expected value of x. Well, the expected value of y is 0. The expected value of x is 0, so the expected value of z is also 0. Now we're going to note that the covariance of x and z is the expected value of x times z, since they both have mean value 0. That's the expected value of x times y minus gamma times x squared divided by the expected value of x squared. And that is the expected value of xy minus gamma times the expected value of x squared divided by the expected value of x squared. Well, the expected value of xy is just gamma. That's how we defined gamma. And this quantity, the expected x squared, is going to cancel out, and it's going to give us gamma. So if we subtract gamma from gamma, we'll get 0. So the expected value of x times z is 0, which means that the covariance of x and z is 0. We're now going to take the expression for z in terms of x and y and turn it into an expression for y in terms of x and z. Then we're going to use that to compute the variance of y. And we're going to use the fact that the mean value of y is 0 to know that the variance of y is just the expected value of y squared. That is this quantity squared times x squared plus twice this quantity times x times z plus z squared. That's just a little algebra. Then that's going to be this quantity times the expected value of x squared plus this times the expected value of x times z plus the expected value of z squared. Well, this expected x squared will cancel one of these expected x squared to give us this. The expected value of x times z is 0, we already figured out. And the expected value of z squared, we don't know what it is, but we do know it is. So the variance of y turns out to be this. Now that I've got a different expression for the variance of y, I can use that in calculating the correlation of x and y. And again, I'm going to make use of the fact that they both have mean value 0. Well, the correlation of x and y is the covariance of x and y divided by the square root of the variance of x times the variance of y. Well, the covariance of x times y is is gamma, and I will substitute this expression for the variance of y. That'll give me this as the expression for the correlation of x and y. Well, I can now use the fact that the expected x squared has to be greater than or equal to 0 because x squared is a square. We're working with real numbers, so x squared cannot be negative, so the expected x squared cannot be negative. Likewise, z is a real number, so squaring it gives a number which is not negative, so the expected value of z squared cannot be negative. This means that the square root of gamma squared plus expected x squared times expected z squared has to be at least as big as absolute value of gamma. It can't be less because this quantity we're adding cannot be negative. This means that whenever gamma is greater than or equal to 0, the correlation of x and y has to be less than gamma divided by absolute gamma, which means it has to be less than or equal to 1. Of course, if gamma is not greater than or equal to 0, if gamma is negative, then we already know that gamma is less than or equal to 1. Therefore, we have shown that the correlation of these two random variables has to be less than or equal to 1. That is to say, it cannot be greater than 1. And that is what we wanted to demonstrate.